Hello, this morning we're going to be talking about density, one of our last standards that we've got in this particular unit. Density is put in this chapter for a couple of different reasons. Number one, because it's a physical property. We just came off a chapter about physical and chemical properties. And then number two has a lot to do with measurement and measurement error and things along those lines. So it's a really good standard to kind of bring together a lot of different things. So I'm starting off with kind of a joke. It's sort of been out there for a while, but which is heavier, pound of feathers or pound of bricks? Go, right? You either say a pound of bricks or you stop and think to yourself, well, if they're both a pound, then they should weigh the same thing. But there's something different about a pound of feather and a pound of bricks, right? A pound of bricks, it's like that big, right? Pound of feathers is like huge. It's a big fluffy, pile of fun. And these two things is what really showcases that difference in terms of what density is. And density is related to not only the mass of an object, but the volume or the size of the object, how big that object is and how much space it takes up. So with density, when we're trying to define it, number one, remember that density is a physical property, not a chemical property, because this is not about how it interacts or behaves. This is something sort of built in, sort of like its color. Density is related to its mass and its volume for a particular size container. It's relatively unique in the sense that most things have a very characteristic density. There's a number that goes along with it that's unique. I'll give you some examples on the next page. And a lot of times they're just different enough that you can kind of tell the difference between what element is just based upon its density. The units of density, because it is mass divided by volume, that's our formula. You can see the formula right down here. Density is mass divided by volume. Our units are mass divided by volume. So we get grams per milliliter is one of our units, or the other one is grams per cubic centimeter. And that's if we've got an actual cube that's 1 centimeter on the side. 1 milliliter is defined as 1 centimeter. So it kind of works out pretty good. Those two are exactly the same unit, grams per milliliter or grams per cubic centimeter, both are the same thing. So again, here's our formula for it. Density equals mass divided by volume. I also want to remind you, if you're looking it up somewhere else, like on the internet or something like that, you may see it occasionally written as P equals M over V. It's not actually the letter P, but it looks a lot like it in text. It's actually a Greek letter rho, but that's what it looks like. So if you see, like in this little joke meme up here, MVP, it's not actually the letter P, but close enough. So density is mass divided by volume is one way that we can write it. And then there's the algebra parts. Don't forget that you can kind of plug in any two of the three and solve for the other one. So you can also get this equation. Again, what all I've done here is I've rearranged and put the volume over on this side. So if I want to solve for mass, I could say density times volume equals mass. Or the last one I can do is if I want to do volume by itself, volume equals mass divided by density. And again, you can kind of see it from this equation. If I solve this one for volume, I can have those three things. So anyway, these are all three the same equations, just algebraic rearrangements of each other. So I'm kind of trusting that as 10th graders, you can do some algebra like this or higher, right? But you should be able to do that sort of rearrangement. Plug in the pieces where they go and be able to rearrange it. So here's some examples of density just to give you some ideas of what density looks and sort of feels like. So I have up at the top here that reminder that 1 milliliter equals 1 cubic centimeter. So when we're saying these volumes, these densities in here, these are all related to a cube that is 1 centimeter on each side or is equal to 1 milliliter of each of these substances. So you can see that there's a range of masses to it. That aluminum is relatively light. It's 2.7 grams per cubic centimeter. It's not very heavy at all. This quarter weighs more than between 5 and 10 grams, just to have some idea what they are. And then if you're talking about something like lead's particularly heavy. It's several times what aluminum is, like 3 times, almost 4 times what aluminum is. It's 11.3 grams per cubic centimeter. So these different masses up here, these different cubes, even though they'll be all the same size, they have a different amount of mass. This one's under 3 grams. The zinc and the iron are in that 7 grams range. These two, the copper is heavier. It's almost 9 grams. And then this block of lead up here is about 11.3 grams. I have down here this gold one is actually not gold, it's brass. And we could tell easily the difference between gold and brass simply based on density. And so sometimes brass is called like fool's gold. There's some other names for, there's pyrite's a mineral that's called that too. And you can clearly tell the difference between these two things just depending on their density. You can see right here, gold is very dense as an element, 19.32 grams per milliliter, one of the most dense elements that we have. The density of brass is different. Brass is a mixture. It's a solution or an alloy made out of copper and zinc. So the actual density of brass is right between copper and zinc. It's right around 8 grams per milliliter if you actually measure it out. And it kind of depends on the exact version of brass that they make. But because it's copper and zinc together, mixed about 50-50, if you want to think of it that way, the average of those two things is somewhere in between. So the density of brass is approximately 8 grams per cubic centimeter or per milliliter, just depending on the exact alloy that it is. But you can tell brass is quite a bit lighter than gold is. And I put osmium on here. Osmium is the most dense of the naturally occurring elements, just a little bit more dense than iridium is. So again, osmium, 22.6 whopping grams per cubic centimeter. It's very, very heavy. You felt it in your hand to be like, whoa, something is really, really wrong with this thing. It's super heavy. I know we just talked about density of solids, but you can also do density of liquids because remember, it's mass divided by volume. So we can figure out the masses and volumes of all of these liquids, no problem as well. And we can actually get, this is a floating density column, by the way. You can see this one right here is water. That's our typical water, like you'd have from your sink. And you know that there's certain things that are heavier and certain things that are lighter. And if you pour this density column really carefully, you can keep the layers from mixing together. So dish water, dish soap, whatever it is, kind of sinks. Milk will actually definitely sink. You got to pour it in there really gently so it doesn't actually mix with the water. But liquid metal, this is a cutting oil. And then like a really dense sugar syrup, this is like Caro syrup, as opposed to oils, which don't mix and then they float on top. Oh, you go away. Sorry about that. But these two will just float up on top. For water, this is an important one, grams per milliliter. Water has a really commonly used density. That's the little joke that I have up at the top. Water is really simple for us to use. It's a nice standard. 1 gram per milliliter is the mass of water or the density of water. So that's an easy one for us to be able to use. And we can use this because then once we know the density of certain liquids and the density of certain metals, we can decide whether or not things will float. So the key here is that if you've got something with a lighter density, it will float on top of something with a heavier density. So here's our friend water right now. And again, this is 1 gram per milliliter. We know what that density is. We can tell some things about all of these other substances that are in here. So we know, for example, that a Lego brick here has a density of less than 1 gram per milliliter. So does oil. It's like 0.8 or something like that grams per milliliter. And we know that cork has even less density than oil is because that cork floats in the oil. Yes, the cork would also float in the water, but it's good to know that the cork is less dense than the oil, which is less dense than the plastic, which is less dense than the water. And then we have things like grapes, which are slightly heavier than water, more dense, and it will sink. And then there's that syrup or like a Caro syrup, super heavy in terms of like almost like molasses, would sink to the bottom. So these things down here, the grape and the syrup, have densities greater than 1, and these other things up at the top have densities of less than 1. This can actually give some really interesting things when you start to talk about densities. When we have certain things, like for example, you can actually have pieces of metal floating in other pieces of metal. This also tells you something about the density of an ice cube, right? You guys know that ice cubes float. If the density of water is 1, you need to know, or you should know, that the density of an ice cube is slightly less than 1, and that's why it floats. Here's a cool visual right here. Anvils floating in mercury. I don't know if you've ever seen this before. I'm going to pull it up really quick. Here it is. That is actually a 100 and something pound anvil, 110 pound anvil. And this is a container of liquid mercury. And you can see that that thing just literally bobs up to the top. It is possible for people to actually walk on liquid mercury, although it's really awkward because it's all smushy. Feels somewhat, I guess, like standing on a trampoline, is what I've heard. I've never stood on liquid mercury, so I don't know. But again, this looks very strange to us because we think of anvils as being incredibly heavy, but yet they are less dense than mercury is. Therefore, they would float in that liquid mercury. All right, moving on a little bit here. More practical stuff. Here's 2 of the kinds of problems that you'll need to get with density. So remember, we always have this equation: density equals mass over volume. there's two kind of types of equations rather than just the typical plug and chug, find the two pieces and plug them in. And this is the water displacement method, and then we have the missing side kinds of problems. So with this water displacement method, a lot of times with awkwardly shaped objects, we drop them in a container of water to figure out what their volume is, because we can't just measure the sides, and I don't know how many milliliters this rock is. So what we do is we take a graduated cylinder, this kind of a tool right here, and we have water in it to begin with, and we plop our rock in it, and when the rock goes up, this is called Archimedes' principle, but the water, the amount of change in volume of the water is equal to the volume of the rock. So again, what we're looking for is what is that value versus what is that value. So this thing right here, delta V, or the change in volume, has got to be equal to the volume of our rock. Our volume of our rock is not 30, and the volume of our rock is not 20. The volume of our rock is the change in volume. So in this case, if I knew what my mass was, I'd kind of do this. Density equals mass divided by volume. I know the mass of my rock, so I'm going to plug that into my top spot, 26.5 grams. I now know the volume of my rock because it's the change. This is 30.0 minus 20.0. You notice how I'm using sig figs in here. And then I can calculate what my volume is. So 26.5 divided by 10 would give us a density of 2.65 grams per milliliter. Again, this up on the top is grams, this on the bottom is milliliters, so our final units is grams per milliliter. So again, it's a matter of understanding that concept of water displacement method to solve for volumes. On the right side, this one depends that you remember a little bit of middle school geometry, which is the concept of how do you find the volume of a cubic thing, a rectangular prism, I think is what they call it. Remember, volume equals length times width times height. So when we're doing density over here we're given density and we're given mass, and we're trying to find the height is our missing piece on this. So plug your numbers in where they go. So density is going to go in this part of our equation, 8.95. This is grams per cubic centimeter. On the other side, we've got the mass right here, 200 grams. And then we've got volume, which is what we're trying to solve. So if we're trying to solve this, the algebra on this one is a little bit funky. This is 8.95 times V equals 200. A lot of times students kind of do the algebra on this one funky. That's why I'm kind of showing it the long way. V equals 200 divided by 8.95. So my calculator says 200 divided by 8.95. I get a value of volume of 22.346. Okay, sig figs wise, let's assume that there's a decimal place here, so we have a couple extra sig figs to go. Otherwise, we only have one sig fig. It's a little awkward. So we'll call this 22.3, and this would be cubic centimeters. Well, now what? Okay, this is the volume of the whole container. So now you can plug that in to your other sides and calculate your missing side. So it's a two-step problem when you're doing a missing side problem like this. In this case, now I know my volume is 22.3, and I know this equals length times width times height. 6 times 4 times whatever my height is. Length times width times height. Again, volume equals length times width times height. I've calculated my volume. I'm now plugging that into my equation and solving for the missing side. So 22.3 divided by 6 divided by 4 gives me a height something along these lines. H equals 0.93, I guess 1 or so by the time I'm doing that. And that would be in centimeters. Notice how these are in centimeters and our volume is in cubic centimeters, cm. So these are two of the types of problems that you'll see with density: the water displacement method for determining volume, and then using volume to determine a missing side. Okay, last little pieces about this. We also approach density a lot of times in chemistry through a graphical sort of methodology, a graphical analysis. And this is what the lab is about. So hopefully you've got a little bit of experience with dealing with this. And I'm going to mention this for a couple of different reasons. One of the big things that we do is when we do measurements of masses and volumes in a lab situation, our measurements are never perfect. And this is this term error, that even if you do it right, you might read the graduated cylinder just a little bit different than somebody else did. Or your scale may be off by just that last digit. There might have been a little air current in there or an air bubble in the water or something along those lines. And I'm not saying mistakes. This is a mistake, right? Way off. I love that. Student needs help. I didn't even make that graph up. But this is something that's obviously not fitting the rest of the trend. These guys all fit the trend, but because this is a science class and not a math class, there's error, just a little bit over under on these things. And that's really, really normal, that even when we use our equipment correctly, there's a little bit of error. So what we do is we tend to plot these on a graph rather than using a single point. Because if I just used one single point, a mass and a volume, I would get a potentially misleading amount of density, a little bit too high or a little bit too low. And rather than mathematically calculating even all of these and doing an average, what we can do is we can plot them on a graph and then do a best fit line. And that's what this is called, the line of best fit. The line of best fit is an average, so to speak, of a data set, an average of two variables. Rather than taking each calculation and averaging it, we can just plot them on a graph. And I'll remind you that we get density from this graph because density equals mass divided by volume. And if we set this thing up right, rise over run is also known as slope. So if we take a look at these two equations right here, we can say that the density of something is equal to its mass over volume, as long as we have the graph set up so that the mass is the rise and the volume is the run. Notice how we've got mass is rise and volume is run. That means the slope of this line right here is equal to density. And that's how we can kind of use density in a lab, or use measurements in a lab with a line of best fit to give us that concept of what density is. And again, just as a reminder, if you're using that slope intercept form, that the y equals mx plus b, m is your density. So if you're given a line equation, that m part tells you what the density is. B tells you that intercept, right, where it crosses, and it should be 0. But again, with our error, that's oftentimes a little bit plus or minus from 0. It should be really close to 0 though. So there you go. We can use this with different materials. And if we know that slope equals density, we can take a look at several different metals, like this is iron, lead, uranium, and platinum, if we did density lines for each one, because, wow, density, that's what I get for talking and writing at the same time, because density is relatively unique, the slope of each line is unique, and we can clearly tell which one has the most density, the highest slope, versus the least density or the lowest slope for it. By the way, this is platinum. This one is uranium. This one right here is Pb or lead. And this one down here is iron. Iron would be our least dense, and platinum would be our most dense. It's got the greatest slope to it. So there you have it. An overview of density, starting with kind of the equation, the concept of what it is, some of the ways that it gets applied, a couple of the different types of problems that you might see, and how we apply it to graphs. So I hope that helped, and I hope you have a great day, great weekend, and enjoy learning about density. See you guys soon.